Okay. I guess Leela is in Colombia, so she asked me to host today. Um, so we got a couple of interesting talks coming up today. Mohammed Jawad is going to talk. Um, I don't know if Jawad has been to any of our previous meetings, but I've been encouraging him, and maybe this will
This
be
is my first time.
this is your first time. So maybe he'll become a regular. Um, uh, I'm going to call him Jawad because we have so many Mohammeds in the department. I have to use their last names. Um, so he's from Pakistan. He got his bachelor's there. Then he did ITU Del no ITU
IHE
Del
Delft is another
ITU Delft,
institute.
right, in water engineering or something like that. And now he's doing his PhD with Go New and Ali Berangi at the U of A, where he's uh, working on several things related to land surface hydrology modeling. He's done some work on evapotranspiration modeling, building a land surface model. I think you'll see an example of it, sort of a catchment scale model using the mass conserving perceptron concept so that it has the state variables, but has conservation based and is getting very interesting results with that. And and then he's been working with me on adapting the KGE metric, as he'll talk about today. And then next week, Jasper is going to talk about his SAGE sensitivity aware gradient estimation um, package that he's been building. I've talked with him and I'm quite impressed. It's a very, very interesting package. And he's work collaborated with Jonathan Frame, and they've shown that they can train models in, I think, at least two orders of magnitude faster by having the explicit adjoint equations for the models processed through his package. Plus, he has a neural net which links static attributes directly to parameters of the model. So he can actually train the model over the entire conus in a few hours or less than a few hours, um, which with the standard PyTorch differentiation, automatic differentiation package takes much, much, much longer. So he's going to talk about that next time. And actually, Jawad has been collaborating with Jasper on getting the new metric and some of his ideas into that Sage package. Anyway, I think you'll find it interesting because I think just like Freddie's, uh, I forget what he calls his package, hydro, the one which allows everybody to use the LSTMs.
I don't know. No, I don't know. No, what is his name? Oh,
Neuro, neurohydrology or something. Anyway, uh, um, I think Jasper's package has the potential to be just like that and even better because it allows you to train conceptual models, continental scale, and in principle should be able to do both machine learning and conceptual and hybrid models when the whole thing is put together with everything automatic, including the data partitioning, uh, block block sampling for the data. And anyway, it's quite impressive. I'll let him tell you about it next week. So with that, I'll turn it over to Jawad.
okay. Thank you very much, Hoshin, for introducing me to the group. Hi everyone. Good morning. My name is Muhammad Jawad, and I am, as Hoshin already mentioned, that I'm third year PhD student in hydrology at University of Arizona. So today I would like to present my work on improved model performance by adapting KG metric to accounting for system non-stationarity, which I have recently completed with the support of my co-authors, Professor Hoshin Gupta, Professor Jasper Baru, Professor Ali Behrangi, Mohammad Farmani, and Professor Goyu Neo. So what is the context of this work? The context is catchment scale hydrological modeling, where we use different types of forcing variables to train a model to predict stream flow at the catchment outlet. And as you know, the main objective is to learn input, state, output relationship such that we get maximum meaningful extraction from the data to predict stream flow at the catchment outlet. In this regard, recently in 2022, Jiang et al. Distributed camel's catchments into various types of categories based on their flow generation processes. So they categorize the catchments into snowmelt dominated catchments, into recent rainfall dominated catchments, historical rainfall dominated catchments, and mixed factor dominated catchments. In this work, to do my analysis, I selected 15 catchments across the CONUS, 3 from each category. Like we selected 3 catchments from recent rainfall dominated from western side. We selected 3 snowmelt dominated catchments, historical rainfall dominated catchments, recent rainfall dominated catchments from western side, from eastern side, and in addition to the work proposed by Jiang et al., we also included 3 arid catchments so that we have representation of all hydroclimatic conditions and all types of flow generation processes. Although I carried out analysis on all 15 types of all 15 catchments, but in my today's talk, I will only be showing the results for 5 catchments, which I have highlighted here, 1 from each category. So the model architecture we used in this study is mass-conserving perceptron-based physical conceptual model, which is a 5-state hydrological model, which takes inputs, different types of forcing variables. I will show you in a minute. And it has a representation of canopy. It has representation of surface snow, upper soil processes, and lower soil processes. The forcing variables we use to train this model are mainly coming from AORC that include precipitation, air temperature, short wave, long wave radiations, air pressure, wind speed, specific humidity. And since we have canopy component in our model, we also use leaf area index from MODIS. And obviously to train the model, we used USGS stream flow. So what is the problem we try to address in this work? But before I go into detail, just look at the flow duration curves of 5 different types of catchments, each belonging to a different hydroclimatic condition. You can see that they are all having different shapes. Some are having very quick recession, some are having very smooth recession. So they all have different characteristics. Even just at looking at the flow duration curve, we can say that they belong to different hydroclimatic conditions. So the problem is when we train our physical conceptual model MA5 using KGE, traditional KGE metric, what we found that the model was giving very good results at high flows. So the high flows in all types of catchments was reproduced very well, but we were having problems when it comes to medium flows and low flows in all types of catchments. Similarly, just like physical conceptual model, we also trained a purely machine learning based model. We trained LSTM model with different nodes, and I'm showing results here with 15 nodes LSTM model. And you can see here that although the performance of LSTM model is better than physical conceptual model, but we again have the same problem that low flows are not well reproduced by the model. And almost in all types of catchments, you can see the same issue. When we look at the flow hydrographs at log scale, you can see this problem very effectively here. You can see that in all catchments, in case of physical conceptual model. The values at low flows are not well reproduced. And similarly, this column is showing the results for LSTM model. You can see that the performance is better than physical conceptual model, but we still have low flows issues in case of wet years. But when we go to dry years, you see that this problem is even more prominent. Even in case of LSTM model, you can see that the low flows it's not well reproduced. So this is mainly the problem which we diagnosed and we try to address. So what solution we propose in our work is that we did some modification to our training metric, and we trained our models again, and we found that what are the improvements we get after we do this modification. So just consider the same slide where I have the flow duration curves, stream flow hydrographs. So this is when I train using KGE metric. But when we modify the metric, you see this blue line, you see that it is coming very much close to the observed line for all flow regimes like high flows and low flows. And also, when we look at these flow hydrographs, you can see that it is fitting very much closer to the observed line for all types of catchments, much better than when we train using the traditional KGE metric. So I will explain in a minute what is that modified metric, but just to show you the results, that how performance gains we got once we did this modification. Also, in case of LSTM model, you see that the low flows and high flows all are well reproduced when we use that metric. And in case of stream flow hydrographs, you can see that the low flow problem is not there, which was previously present when we trained the model using KGE metric. So what is the reason of the problem? The reason is when we use Gupta efficiency KGE metric, which is having three components: long-term mass balance, variability around that long-term mean, and correlation component. So when we select this metric, we assume long-term mean as a benchmark, right? And we ignore the non-stationarity in the system, and we only focus on long-term mean. So due to which, what happens is that when we use this metric to train our model, the model is forced to match this mean and variability around it, and also the correlation component. And as we know that the mean is mainly focused by the high flows. So it is the long-term mean is controlled by the high flows. So the model tries to fit high flows very well, and the low flows are not well reproduced by the model. And the same thing I have shown previously in my previous slides, that when we looked at the flow duration curves, the low flows were not well reproduced, but the high flows were accurately reproduced by the model. If we look at the environmental process, sorry.
Jawad, sorry, if I could just jump in. One thing you and I forgot to discuss when you were preparing here is we also tried in the early days of this work shifting it to the median or to other quantiles.
Yeah.
And we should have mentioned that, but it didn't fix the problem. Yeah.
Yeah. We tried different things. I mean, if we do not incorporate non-stationarity thing, we do not get good results. So as Swashin mentioned, that we tried different things like long-term median and all these things. So the problem was still consistent. So what is the problem? If we look at the environmental processes like rainfall and stream flow, we know that they are not stationary in nature. They are having non-stationarity. Some seasons have high flows, some seasons have low flows. So unless we explicitly incorporate that non-stationarity into our metric, we cannot reproduce good results for all types of flow regimes. Just take the example of two catchments from my study area. One is historical rainfall dominated, and one is arid catchment. If we look at the hydrological drivers, if you look at this air temperature, where the darker line is showing the 91-day moving average, and these dash lines are 595 quantile bounds, you can see there is some type of stationarity in the system when we talk about temperature. But when we look at precipitation, you can see that it is highly non-stationary. And also, if we look at stream flow hydrographs, you can see that they are also non-stationary. Some years having high flows, some year having low flows. And the similar thing is with the runoff ratio, it is non-stationary in time. So consider this increasing system. So for example, if I have to represent a benchmark to represent this system, long-term mean is not a good option to show. At the least, what I should do is to remove the pattern from that signal. Or even better option would be I select a benchmark which is passing through the signal and it is taking care of all types of ups and downs, high and low values. So the thing is, what approaches we should use to select non-stationary benchmark? One very common thing we can do is moving average mean. So consider this figure where the green line is showing the observed flow and this black dashed line is showing a long-term mean. To represent a non-stationary benchmark, we can use time-centered moving average of different window lengths. For example, we can use 365 days moving average. We can use 181 days moving average to show the non-stationary benchmark. We can use 91 days, 61, 31 days. So what you can notice here is that as we reduce the window length, the benchmark is getting much and much closer to the observed stream flow. And it is picking all the high flows and the low flows much better as compared to the longer window lengths. Another approach we can use is fixed section-wise mean, where rather than using moving average mean, we fix a period like, for example, 365 days, we take the mean, and then next 365 days, then next 365 days. In this way, we can have another option for non-stationary benchmark. We can use some other section lengths like 180 days, 90 days, 60 days or 30 days. So just similar to the moving average approach, as we reduce the section length, we can see that we are having representation of our type of characteristics of the signals very well when we reduce the section length. So again, just consider here the non-stationary mean with both the approaches like section-wise approach and the moving average approach. For 30 days, you can see this non-stationary mean, and this black line is again showing the long-term mean. This red dash line is showing long-term standard deviation. So the question is whether only the mean is non-stationary or we also have the standard deviation non-stationary. In this plot, you can see non-stationary standard deviation, so that you can see that it is also varying in time, that it is also not staying constant. And one more thing we can observe here is that as we reduce the section length, for example, from 365 days to 180 until we go to 30 days, the relationship between mean and standard deviation gets closer and closer to 119. As you can see here, in case of section length of 30 days, it is much along the 119. And here, in case of when the section length is longer, it is not along the 119. So what is the impact of non-stationary benchmark on distribution of anomalies? So here you see the distribution of,
So what?
sorry,
Sorry, define anomaly to people.
yeah, anomaly, it is the observed signal transformed. We transformed it on the log scale, and um, we then we compute the benchmark using the section-wise approach. And then we took the difference between signal minus benchmark and divided it by the standard deviation. So that is what we call the standardized anomaly. And you can see here the red line showing the distribution of anomaly, and this black line is showing the double exponential. I will show later that why I put it here. But what you can observe here is that when we use long-term mean as benchmark, the distribution of anomalies is not smooth. It sometimes it has skewness, sometimes it has bimodality, and it is of very irregular shape. As we reduce the section lengths to 365 days, still we didn't get any improvement on distribution. If we further go down, you can already see that in some types of catchments like snowmelt dominant catchments, it starts to get improved and well behaved. We further reduce the section length. We see that for all types of catchments, it gets very well behaved as we reduce the section length until we reach a very small section length of 7 days. You can see that it is almost fitting very close to a double exponential curve. So here we introduce the metric. We call this Jawad-Kling Gupta efficiency is the name proposed by Hossein. So it is just like KGE metric, but instead of using long-term mean as a benchmark, this time we have option to use non-stationary benchmark. And just like KGE metric, we have three components here, M star, V star, C star, where this M star is showing the non-stationary mean. V star is showing the variability around that non-stationary mean, and C star is showing the cross correlation. And if the model is perfect, it is just like the KGE metric, it will give us the score value of 1, and the lesser value is showing that the model is not producing good results. It is just very similar to NSE and KGE metric. So what are the results we got when we use this metric to train our model? First of all, I will show you the impact on flow duration curves. So when we selected a longer section length of 365 days, you can see that with JKGE and KGE, they are performed almost very close to each other. There is almost no difference between using JKGE or KGE metric. But as we reduce the section length, you can see that the improvements starts to come, but we are still not there. As we further reduce the section length to 90 days, we see a little more improvement on some type of catchment like arid catchment. As we go to 30 days, we can see that we have a very close to the observation line for all types of catchments. And if we go further down, we reduce the section length. We see that there is some type of degradation on high flows in some types of catchments. The same is when we reduce the section length to 1 day. That was the extreme case. So what we found through our analysis is that if we select a section length of 30 days, that is the optimal length, but this is still the hyperparameter. We have to take care about that, which section length to select. But our analysis on 15 catchments show that if we select this section length, we are having good results on all types of catchments. Similarly, if we check the the impact on streamflow hydrographs, you can see that for the wet years and for the dry years for model architecture MA5, you can see that we have the model is reproducing high flows and low flows very well. In case of JKGE, which is blue line, and in case of KGE, we are, as I already explained, that we are having problems, and we see consistent improvement when we use JKGE on all types of catchments for wet years as well as on dry years. But in case of dry years, the improvement gains are much more as compared to wet years. And these are the results when we use, in case of machine learning, LSTM15 model. Again, here you can see that we have much better results when we use JKGE metric on all types of catchments in case of dry years, but also it reproduces very good results on wet years. So other than that, we plotted some other diagnostic plots like monthly bias, QQ plots, and scatter plots. So I explain what are these things. For example, if you look at this first column for 5 different catchments, this is percentage monthly bias for 8 water years. So where this is the 0 line. So if we stay closer to the 0 line means the model is better. You can see here the blue line for JKGE is much closer to the 0 line for all types of catchments, although it has some higher percentage bias for some catchments, but still we have better results as compared to using KGE metric for all different types of catchments. Again, if we look at the quantile plots, which is this column of the figure, you can see that the high flows are well reproduced by both the matrix, KGE and JKGE, but the low flows are having issues in all catchments. And the same thing is seen here in case of scatter plots, where the low flows in case of KGE are underestimated. But in case of JKGE, we are having very much along the 119. And here in this panel, I'm showing for which months I am plotting the mean monthly observed on x-axis and monthly bias on percentage on y-axis to see that which type of flows has they have higher percentage bias. And we can see that the low flows are having more higher monthly percentage bias as compared to high flows in all these catchments. And a similar story can be seen here in case of machine learning LSTM model, that the monthly percentage bias with JKGE is well reproduced as compared to KGE metric. But in case of QQ plots, you can see that in physical conceptual model, we were having underestimation of low flows, but here we see there is overestimation of the low flows, but high flows are well reproduced by both the matrix. The same thing can be seen here in scatter plots with KGE metric and JKGE metric, where in case of KGE metric, you can see that the low flows are not well represented by the model. And in case of JKGE, we are having consistent better performance on all types of catchments. And similarly, again, we can see here that the low flows, the low flow months are having higher monthly bias as compared to the months with high flows, high mean flows. Now, as you remember, I explained 2 approaches to compute non-stationary benchmark. One of them is section-wise approach, and the other one is moving average approach. So in order to select which one we should use, we carried out our analysis on different catchments, and we found that for the longer section length, we have somehow different results. But as we reach to the section length of 30 days or the window size in case of moving average approach to 31 days, we are having similar performance in case of both approaches, but the benefit of using section-wise approach is that its computational cost is quite less as compared to moving average, because in case of moving average, at every time step we have to compute the mean. So we through our analysis we found that there is no difference between using both approaches when it comes to the results. But for efficiency point of view, section approach is better than moving average approach. So other than that, what we did is we carried out model ablation studies. So where instead of using the complete MA5 model architecture, we removed some of the processes. Like in case of MA3, we removed the canopy component and we call that MA3 model architecture. And we have another ablation where we also removed the base flow tank in addition to canopy, and we call that model architecture 2. The reason to do this analysis is to see if the performance is consistent. If we ablate the model architecture, can we get the same better results as compared to KGE metric, or it is, I mean, the impact of the model architecture? And the same thing we did for the LSTM model. We use different nodes like 15, 10, and 5 nodes. You can see the flow duration curves for the physical conceptual model and LSTM-based models. And you can find that in the ablated versions and the full model architecture. In case of physical conceptual model, we are having consistent better performance when we use JKGE as opposed to using KGE metric for training the model. And the same story we can see from these figures of LSTM model, that we have consistent gains irrespective of the number of nodes when we use JKGE metric, although we have better results as compared to physical conceptual model, but for some of the catchments, we get gains on low flows when we use JKGE metric. So other than that, we also compared different metrics when we trained using JKGE and when we trained our model using KGE. For example, in this panel, you can see KGE metric and its components, where the values higher, where the values closer to 1 are better. This V prime is actually 1 minus V, and M prime is 1 minus M, and rho is a correlation. What you can see here is that in all these 4 metrics, they are very less sensitive to the choice of the metric. You can see here the KG values are staying much closer to each other, irrespective of the choice of the metric for training. Whether it is JKGE or KGE, we get consistent results of KGE. There is small variation in case of variability, but if you look at the scale of X and Y axis, the scale is very small. So almost the same values we get when we use KGE as a training metric or JKGE as a training metric, and also for the M prime and the correlation component. But opposed to that, when we look at the JKGS and its components, we see that they are sensitive to the choice of the training metric. For example, here, if you see here, when we use KGE as a training metric, we get poor performance on JKGE, this variability is less or more less impacted. But if you look at the non-stationary mass balance, you can see that when we train using KGE metric, it is not well reproduced by the model. It is, I mean, it is telling the same thing as I have explained earlier, that the low flows and the medium flows were not well reproduced when we use KGE as a training metric. So here in this figure, you can see all of the 8 metrics, that how they're performing when we use different metrics to train our model. So now, other than that, we also carried out component augmentation study. So in this figure, you can see 8 different metrics where the value closer to 0 is better. So KGES prime and JKGES prime is actually the 1 minus KGES prime. And the ideal values for V, C, M, and V star, M star, and C star are closer to, I mean, the ideal values are 0. And I plotted the metric values on. I took the square root just to highlight the small differences that how they are. Um, so you can see here that when we use JKGE as a training metric, these are the blue lines. These are the blue points showing when I use JKGE as a training metric, and the red dots are showing when I train using KGE as a training metric. In this case, I mean in all three catchments, you can see that the long-term mass balance is a little bit disturbed. You can see that these blue dots are a little bit higher when we train with JKGE metric. But when we included the long-term mean as an additional term into our metric, we found that we got that improvement on JKG. I mean, this time the long-term mean is also well reproduced by the model in all the catchments. Other than that, augmentation studies, we also carried out component ablation, where we found whether if we ablate any component from the our formulation of JKGE, do we get any degradation or not? So for that, what we did is first of all, we removed the correlation component, which is C prime, and we checked the impact that whether we get the same results or not. But we found that if we remove that term, we get poor performance on that. And also in another version, we call that ablated version 2, when we also remove the variability term, and we found that we are having poor results on variability also. So what this figure is telling is that we should have the representation of all the components. I mean, all of the components are equally important, and we cannot say that this component is not important, and we can omit that from our formulation. Another important experiment we did is to check whether if because we found that we are having problems on low flows. So what we did is to train our model after log transforming the flows. Here you see the flow duration curves for 5 different catchments, where the blue line is showing JKGE with 30 days section length. And this red line this time is showing the KGE as a training metric, but on the log transformed flows. So what we see here is that the low flows are well reproduced if we transform the flows on log scale. But what happens to the high flows? Look here, the accidence probability range of 0 to 5%, which is showing the high flows. So we are having poor performance in case of log transformation. But the JKGE is producing good results for high flows as well as low flows. The reason is that we account for non-stationarity in the mean of the flows. So what are the conclusions of this work? The stationarity assumption is invalid. So non-stationary benchmarks are necessary to incorporate. And if we really want to have good performance, we should incorporate the non-stationary benchmarks rather than simply relying on the traditional long-term mean as benchmark. JKGE allows flexible benchmark selection, although I showed here 2 types of benchmarks option. One is section-wise approach, another one is moving average approach, but the formulation of JKGE allows for the selection of any type of benchmark, which is even better than these. And we found that if we do that, we get improved information extraction from the data. And also explicitly accounting for non-stationarity improves performance across all flow regimes. So it is not like we are having better results on low flows or medium flows. We are having the better performance on all types of flows, high flows, medium flows, and low flows, if we incorporate non-stationarity into our metric. But the major improvements we have seen in low and intermediate flows, preserving the high flow accuracy because the high flows are already well reproduced when we use the KGE or NSE metric, but we are having problem at low and intermediate flows, and that problem is resolved using this JKGE metric. And in our study of 15 catchments, what we found is that the optimal window length is 30 days, because if we go beyond that, I mean, if we further reduce the section length or window length to 7 days or some other length, so we start to get degradation on high flows. So we recommend so far, based on our analysis, that 30 days is optimal window length we can use. And as I explained that if we compare moving average and section-wise approach, there is no significant difference. So we should select section approach because computationally it is efficient as compared to moving average approach. And also JKGE improves time varying mass balance. You remember the plots where I showed that the non-stationary mass balance is very sensitive to the choice of metric. So if we use JKGE metric, we get much improved time varying water balance. So we get consistent gains across model types, whether it is physical conceptual models or it is LSTM models. So our analysis shows that we get consistent performance on all types of model architectures, and also different types of ablations. Like if we simplify the model, we get the consistent better performance in case of JKGE as compared to KGE metric. And also we get consistent gains across diverse hydroclimatic regimes. You remember I have different types of catchments belonging to different hydroclimatic conditions, and we get consistent improvement on all catchments, whether they are humid or arid catchments. And we also found that all the JKG components, whether it is non-stationary mean, whether it is variability or it is cross correlation, they are all very important. And if we take out any of these terms, we get poor performance. So we should incorporate all of these components in the formulation of JKGE. And we also recommend that we should, in addition to these three components, we should incorporate the long-term mass balance component also to preserve the long-term mass balance as well. So that way we are having better performance on non-stationary mean and stationary mean as well. So what are the next steps? Thankfully, Jasper incorporated our JKG metric into his Sage application. And the objective of that is to run different types of models on all the camels catchments, and to see that what performance gains we get if we use this improved metric on different types of models and on different types of catchments. So that work will continue in that direction. So thank you very much for listening to my presentation. And if you have any questions, you can ask.
All right. Great job, Jawad. Thank you. We actually have a Notebook LLM little publicity video for this. I might play it for you guys later, but let's see if anybody has discussion or questions for Jawad.
I have a quick question. So when we use like mean squared error or something as a metric, um, I think in, Freddie's code and other people's code, they always kind of normalize in space just because, I guess wetter catchments will have higher stream flow and more uncertain catchments will have a higher error. So you want like to treat all catchments in the same way when you're training um, on multiple catchments at the same time. So I wonder how the JKG does in terms of treating everything fairly in space as well as in time.
Right. So, so far we have only carried out its temporal non-stationarity, but if we have to consider spatial non-stationarity, obviously we should incorporate the statistical properties of each and every catchment individually. I mean, for catchment A, we should use its non-stationary mean and then use non-stationary mean for the catchment B as well as. So I think that way we can have the balanced impact of this non-stationary thing on spatial as well as on temporal thing. Because what I know is that when people use the metric for all the catchments combined, they use the mean for each catchment individually, standard deviation for each and every catchment, and then they train the model. So I think that way we can have the representation of non-stationarity in spatial terms as well as in temporal terms.
Right. So as long as you capture the temporal variability individually for each catchment, then you think the JKG will automatically account for the spatial
Yeah.
variability. Okay.
Yeah, because what I think is that spatial variability is somehow, which is already somehow incorporated by people when they train catchment scale model. But temporal non-stationarity is something which was missing, and it is very important to incorporate that.
So strictly
Hmm.
speaking, it's already there in the JKGE. You just have to make sure that every catchment is subtracting its non-stationary mean and dividing by its variability. Yeah.
Yeah,
That's why we're focusing on anomalies. Yeah.
I have a question.
sure.
I- Yeah, in general, when you train with the KGE, or well, in that case, your metric, is that the problem is that you can have this kind of period, especially when you are working with arid catchment, where you have maybe zero flow, or maybe you
Yeah,
have a constant value for maybe, I don't know, 3 months. So in that
right.
sense, you are have your metric itself is going to be undefined. So how you are dealing with that?
Yeah, in case of zero flows, we should be careful about the denominator term. We should incorporate some type of epsilon term there so that we do not have the problem of gradient explosion and this thing. And Yeah, we should be careful about the zero flows things because they are very critical, I think, to incorporate.
In fact, didn't it happen, Jawad, when you reduced the section length to be too small, you started to get gradient explosion.
Yeah, yeah, yeah,
So partly having a 30-day helps, but if in
yeah, yeah,
fact, yeah, but if
yeah,
in fact you can have 30 days of zero flows. So in that case, we need a flag, and then you have to put a small
exactly.
epsilon in. Yeah.
So, um, very nice work, Jawad. So, as you know,
Thank
we've
you.
been implementing the metric and playing around with it on all these catchments. Yeah, so this zero flow is an issue, but you can, if you reformulate M, then that problem is resolved, I think. But the thing I wanted to say after thinking about all this, just a way to think about it, I think, is that essentially you realize that, and this is always something a colleague of mine tells me, who's a statistician, a physicist, and he always tells me, Jasper, your conditional mean is different at each time step. So you should really look at discharge as being a random variable. At each time step, it's a different random variable. Its mean is different. Its shape is different. And I think the realization in the work that you've done is, and that also comes out in the reformulation, that we should be looking at two different metrics. Essentially, your M is an NSC of the mean, and
Mm-hmm.
the other NSC, if people want to think about NSCs, is then about the anomaly.
Yeah,
So we separate the normal metrics, combine that all together in one value, but essentially you're now separating out those two spaces. And I think if people reanalyze their data, they're going to see that on the dry catchments, that NSC of the mean is really poor. So
right,
it's really difficult to track where is the, and so I think that separation, that realization is extremely important, extremely valuable. There,
right,
the, and what you already mentioned also in our communication, because you now look at the non-stationarity of the mean as a metric, your JKGE values are just going to be much lower than what people are used to with an NSC,
right.
a KGE. But I think this is a really, really important paper, just making the, you could say arguably simple, but that's how most steps forward, bigger steps forward are. Ultimately, you sit there like, why didn't we do this 20 years ago? But I think the realization that the mean of discharge is not constant. And that's really simple, but the consequence then is that your metrics should reflect that. I think that is a
Exactly.
really important, and then you can build 10,000 metrics, but just separating those two spaces, that's a really important. So I thank you for that.
Yeah, thank you for, yeah, that is very, very important point to highlight it that we should also take care about the NSC of the benchmark as well. So we should report that that how is that performing so that we get to know the idea about that how is non-stationarity around the mean, long-term mean.
And if you use the JKG for a lot of watersheds, then ideally you should not run into the problem that for all these camels basins that it starts to emphasize those with very large variability because the residual sum of squares is so large, right, for
Right.
those basins. So you should start to see that wetter and drier basins more or less get an equal weight in the estimation of the network weights, biases, or whatever you're doing. So
That's right.
yeah.
Yeah, that's right. I think Jonathan Frame has question.
Yeah, hey, thanks for the presentation. Um, I guess I talked to Jasper about this a couple times, but then the each sample being independent made me think of it. Like let's say we're using a model to make a forecast of like the next 3 weeks. So we have a time series of the next 3 weeks, and then if we get the realization, we have the observation of the next 3 weeks. What I've been kind of struggling with is should we be using that mean of the realization to assess the quality of our model prediction because we don't know the mean ahead of time. And I wonder is like, so I think that like I agree this is like a simple thing that like, yeah, why weren't we doing this before. But in the situation where you don't know, most of the time we don't know the mean. I mean, like ungauged basins, for instance, we don't know the mean. Is there any room to extend this to like other? I mean, like we can normalize it by other values. That was a whole topic of conversation, like normalizing by the variance of like a large sample or something like that. But in a lot of situations where we're running a model, we don't know what the mean is going to be, including in a non-stationary condition. You don't know what the mean, even if you have historical data, you don't know what the non-stationary trend is going to do in the future. So I'm just wondering if
Yeah, I think is that so there are two parts. One is model training and the second is model evaluation. So far what we have done is that we try to illustrate we should because when we train our model, we have to tune our parameters in such a way that they do not give, I mean, they give equal emphasis to all types of flow regimes. So that is what we did using this non-stationary mean. And of course, if we have to evaluate our model, then we can have the similar type of thing which we can use. But yeah, I'm not sure that what is the answer to if we do not know the mean in the future. So how to compare with that one? I still don't have answer for that. Sorry about that.
But that holds for all metrics, right?
Yeah.
That problem. But I think this is training, right? And then so then you get the parameters, and then you hope that with these catchment attributes, that your evaluation for catchments where you don't have data, right? Supposedly you don't use that for training, also gets better.
I think it's important to so you're making a distinction between training and evaluation, which is excellent. But it's important to remember that there's two sources of system non-stationarity. There's non-stationarity in the structure of the system, and there's non-stationarity in the forcings or the drivers. And because we're training a fixed model with fixed parameters and fixed architecture, we're assuming that the system itself is stationary. The architecture of the system is stationary. In other words, there is a data generating process which is predicting the mean. So the non-stationarity we're referring here has to do mainly with non-stationarity in the drivers, which are causing the streamflow. But that doesn't mean that we can't use this approach even if the system itself is non-stationary. You just have to build in the ability for the model to change. Like, you put in a dam, you need to put in a representation of a dam into your model, because the assumption always is that you can represent your data generating process using a fixed set of equations which don't ultimately change with time. The thing we're talking, and if you believe the laws of physics are fixed, then essentially there's no such thing as non-stationarity per se on the total scale. So what we, as Gray pointed out once, this thing of non-stationarity really is an issue of the model. Is the model capable, or does the model have to, vary in time in order to track something that because of model misspecification over there. But I think the main point here is that during training, you want to extract as much information as possible. And then if you've done that during training, then hopefully during evaluation, your model will behave better. But if the system changes its structure into the future, then you have to figure out some way to predict that. And that's not, no training metric is going to help you with that.
Thank you, Hoshin. I think Luis has a question.
Yes, I have one. Kind of first, I need to know, just to know how did you do it. But are you training in a sequential way, or you are just training kind of random when you did your experiment?
Yeah, so it was not sequential. It was stratified training and evaluation. So we did like the classification based on extreme years pairs, and we classify based on that, such that we have the representation of high flows, wet years and dry years in training period and in evaluation period. So we stratified based on yearly data.
Yeah, but my question go inside when you are doing, I know, backpropagation. What is go inside of the batch is a sequence of the continuous days or a kind of
Yeah, it
randomness
is.
inside.
It is sequence. It is not random.
Yeah, because this was exactly my point. I was thinking that was in this way. So, and generally in machine learning, you are always trying to randomize everything. So I don't know if it's exactly the same, but from my understanding, basically what we are saying is that we need to account for the change in the mean and the standard deviation in the time series that is changing on time. So could be the same if the data before training, I maybe I could standardize that using a kind of a mean, a
Right.
varying mean standard deviation that is varying on time. So basically, after that, really, I could use kind of any metric because already my data is standardized using this idea.
Right,
Could,
right, right.
could that be the same?
Yeah, actually, I did not did the training like splitting into multiple batches. So it was one complete batch, and in that batch, I did the training like computing each and everything. So it was sequential. So it was not something like splitting into mini batches and these things. So that thing I did not try in this work.
But you did, so you're correct, Luis. You can calculate using a moving window, you can calculate a mean at every day and a standard deviation at every day. And you could pre-do that before you do any model training, right? Um, and the standard deviation will change. So if you look at the anomalies, the anomaly standard deviations are different for every month, so to speak. Jawad did try putting in a non-stationary standard deviation also into the metric.
Yeah.
Right now, we're just assuming all the anomalies have the same standard deviation, even though that's not true. Because if you take out the variability of the anomalies, you'll see that it has a small, then it gets large and small and large and so on. So strictly speaking, you should divide by the standard deviation at each time step, and then you
Every
would
time
get a
step.
homogeneous sequence. Um, Jawad did try that, and it did not improve the training per se. That's not to say that in some other problem that might not actually be a good thing to do. It's just that in his experiments, adding a non-stationary standard deviation didn't actually result in any further improvement.
Yeah. Why I was asking that because for sure, yeah, we can basically you are saying we have to modify the metrics, but maybe we could in another cases we could modify the standardization of the data. Because I was
Exactly.
thinking that another kind of I have been working a lot with random forest, for example. So the metric in random forest is not KGE, and I cannot implement KGE there directly. So maybe could I standardize the data in kind of following the same idea that you have now?
I think it makes sense. Yeah. Joe?
Okay, we have to try.
Mhm.
Yeah. My question is about the reasoning behind like why you think this works. So clearly the models can fit the data across all these, low flow to high flow to medium flow. But it's just not. So is it due to like vanishing gradients in these low flow components or poor
Jawad, can you put up the
optimization
metric page? Yeah.
or
Yeah.
Which slide you?
The JKGE metric formulation.
Okay.
because I think you showed that the the high flow fit doesn't really degrade, right?
Correct.
It's still getting, yeah.
Can you put that full screen, Jawad? Do you mind if I take this question?
Yeah, you can.
Yeah.
It's not bad.
Just show that. Um, so if you look at the M star term, Joe, you'll see that it's if you just rearrange terms, it's BTO minus BTS over BTO. Yeah, and then a whole squared. So if you take out the denominator BTO squared, you will see is that essentially you're matching the two benchmarks, the simulated and observed benchmarks. Sorry, time varying means. And the weight that you're giving them is the weight would be 1 over BTO squared. Yeah.
Okay.
So when BTO is small, the weight is large. And when BTO is large, the weight is small. So essentially, we're not doing anything terribly different from a weighted least squares. But the question was what to choose as the weight. And here it just turns out.
Right.
Now you could change that. I mean, we're using a squared anomaly. You could use a power of 1 using an absolute value, and you'd get a different, or you could use a power of p, right? In which case the KGE there would be a pth root rather than a square root. So we could generalize this, and the p power becomes another hyperparameter that would have to be varied just like the 30-day section length.
See.
So, but I think the key is to notice that go to the time varying anomaly means to what?
I'm very
No. Go forward all the way to where you're showing the scatter plots and everything. Yeah. No, the scatter. Just go back. Yeah.
back.
You had it right now. The scatter plots and the time series of anomaly means.
Okay. Yeah, this one.
And so my sense, Joe, is that what's happening is we're normally trying to track water balance over the long term. And then you could try to, if you do annual Nash efficiency or an annual KG, you would be tracking water balance over the annual time scale. Essentially now what we're doing is we're tracking water balance over the monthly time scale. So the blue line over there is showing that you're forcing the monthly water balance to be perfectly matched because you're explicitly representing it in the metric. So you have a time
Well, that
variable.
wouldn't be good for snow-dominated regions, so.
And that's why the window size might have to be different for different kinds of hydroclimatic zones.
Mhm.
But even in a snow-dominated region, dx by dt is input minus output, and you want effectively to match dx by dt in the model to dx by dt in the actual world, right? And you could match that on a daily time scale, a monthly time scale, a weekly time scale, whatever you want. I think
Yeah.
effectively what this is doing is it's saying we're not willing to tolerate deviations in the water balance which are larger than a month.
Right. But my question is more like, why doesn't KG work in low flow regions? Like making the fit in low flow regions better would improve KG, but it's just choosing not to do that, right?
Because the error in low flow regions is so small that there are many ways to match the long-term mean, and you can get the low flow values. Small absolute deviations in low flow values are actually large relative deviations, and they don't change the metric very much because the metric's not terribly sensitive to those small
Yeah.
things.
Okay. They don't change it very much, but they change it, right? So why isn't it
Because it's
doing
dominated
that
by
eventually?
the high flows.
Right, but you're showing that you don't have to, you're showing that there's not really a trade-off, right? Like you're not degrading the performance of high flows. You're just improving the
So
performance of lows.
this depends. This is what you're saying, Joe, is that you're assuming is the parameters that match the high flows will also allow the low flows to be matched, which might not be the case. But I agree with what you're saying in like a deep neural network where you would think that you could find a set of the 40 million parameters that you have that should be able to match both of them, but they simply don't. So I've always kind of wondered about that too.
I think
Okay.
it would eventually, Jonathan, if you just forced it to continue training, but you eventually stop, right? And the gradient becomes very small, and you just give up. I think if you continued on and didn't give up, you would eventually find a
We should
good.
set up a computer to just train on one basin for like years and see what happens.
Sure.
I think I have an idea pertaining to that. So yeah, we can talk about that later, maybe.
Could
I
be
mean,
like one of the light bulb that never goes out. We'll have the model that never stops training.
yeah. I mean, ultimately, if you put mean squared error in and you train it, it should eventually get there also, if you have enough degrees of freedom. Yeah.
Yeah.
In the conceptual models, you don't have enough degrees of freedom. So, yeah.
Okay, thanks. I have to go, but
Um, if you guys will put up with it, I was just going to show. So, you guys are familiar with Notebook LLM, right? The new Google thing. So I stuck the paper into Notebook LLM, and it'll make a PowerPoint for you, which we didn't use. It'll also make a little video for you. I'm going to play you the little video it made when it read this paper. I thought it was quite impressive, but I just could show you as an example because you guys might want to play with it. Okay. Can you guys see the moving a modeling target?
Yeah, that's too zoomed in.
That's just the way it is. It's
Oh,
not
okay.
yeah.
Gotcha.
It's going to go away. Let me just hide the floating controls. There we go. And tell me if you can't hear it.
All right, let's talk about one of the biggest challenges we face in hydrology today. We're all trying to model our planet's water systems, right? But the problem is, the planet won't sit still. With climate shifts and land use changes, we're basically trying to hit a moving target, and that makes predicting our water future incredibly difficult. And really, this is the question that keeps us up at night. I mean, everything from managing our reservoirs to issuing life-saving flood warnings depends on getting this right. But how can we be confident in our forecasts when the fundamental behavior of the environment we're modeling is changing right under our feet? So let's really get into the weeds on this. You know, the root of this whole issue comes down to a really basic assumption that's kind of baked into a lot of our traditional tools. It's something we could call the stability illusion. And this isn't just a small flaw, it's a crack in the very foundation of how we've been building and testing our models for years. That core assumption has a name: stationarity. Put simply, it's the idea that the past is a good predictor of the future. It assumes that the statistics we've observed over the last 50 or 100 years, things like average rainfall or river flow, are going to hold steady. And for a long time, look, that was a pretty reasonable way to approach things. It made the math work. But here's the thing, this isn't a new problem. This landmark paper from Science called it out all the way back in 2008. They said, point blank, that stationarity is obsolete. The climate is changing, we're developing land like never before, and because of that, yesterday's weather just isn't a reliable guide for tomorrow. Our world is non-stationary, period, and our tools really need to catch up. So what does this actually mean for us in our day-to-day work of building and calibrating models? Well, it means we've basically been measuring our own work with a broken ruler. The very benchmarks we use to decide if a model is any good are built on that same shaky, outdated idea of a stable world. And don't get me wrong, our tools have gotten way better over the years. We started with the classic Nash-Sutcliffe efficiency, or NSE, back in the 70s. Then, in 2009, the Kling-Gupta efficiency, or KGE, came along and was a huge leap forward. It's a go-to for so many of us now. But here's the kicker. It secretly carried forward the exact same fundamental weakness. And this right here is the heart of the problem. Metrics like KGE are designed to answer one question. How much better is my fancy, complex model than just guessing a long-term historical average every single day? And in a world that doesn't change, that's a perfectly fair question to ask. But in the world we actually live in, it's a deeply flawed way to measure success. This slide just lays it out so clearly. The old way, the KGE way, judges everything against a single flat line. It's completely blind to seasons, to trends, to the fact that one decade might be way drier than the last. The new approach, though, it's about using an adaptive benchmark, one that actually moves with the system's real behavior. It's just a much smarter, more context-aware way to grade our work. Okay, so that brings us to the really exciting part. The solution that this new research is putting on the table. It's a brand new metric built from the ground up for our non-stationary world. It's called the Jawad-Kling Gupta efficiency, or JKGS for short. And its core idea is actually pretty simple, but it's incredibly powerful. It just throws out that old static long-term average, and in its place, it uses a dynamic benchmark that actually learns from and adapts to what the system has been doing lately. So how does it pull this off? Well, instead of one average for the whole period of record, it calculates a moving average, let's say over the past 30 days of real data. Right away, this gives you a flexible baseline that rises during the wet season and falls during the dry season. Then it scores the model based on how well it predicts the little wiggles and jumps around that much more intelligent moving line. So that's the theory, and it sounds great, but does it actually make our models better? Well, the researchers put it to the ultimate test. They set up a head-to-head competition. Train one model the old way, train an identical model the new way, and see which one performs better in the real world. And honestly, the results you can see with your own eyes are pretty stunning. What we're looking at here is a model for a wet river basin. The black dots are the actual observed river flow. The red dashed line, that's the model trained the old way. Now look at that solid blue line, the one trained with the new metric. Just trace it. See how much better it hugs the real data, especially in those valleys. Those are the crucial low flow periods, and the new model just nails them in a way the old one can't. And if you think that's impressive, check out what happens when you move to a really tough, arid climate. Look at the plot on the right. The old model, that red line, it's a mess. It's predicting tons of water when the river is nearly dry. It's basically useless for water management. But the new model, the blue line, stays right on track. It actually captures the behavior of a system that's notoriously hard to model. So the charts look amazing, no doubt about it. But when you dig into the hard numbers from the study, the story gets even more dramatic. Let's go back to that arid catchment we were just looking at. When the model was trained using the new JKGES metric, it ended up with a pretty solid score of 0.67. Good performance. But now look at this. When the exact same model was trained using the old metric, its score, when judged by this new, smarter standard, was negative 0.11. And in our world, any score below 0 means your model is literally worse than a dumb guess. It means it completely and utterly failed. So when you put all this evidence together, the conclusion is pretty hard to ignore. We might really be looking at a new gold standard for how we develop and evaluate our models from here on out. So why is this a better tool for us? Well, for one, it flat out improves accuracy, especially for those critical low flows that we care so much about. It's way more robust. It works great in all kinds of different climates. It's also versatile. It helps both our traditional physics-based models and the newer machine learning approaches. And maybe most importantly, it lets us avoid some of the, let's say, creative workarounds we've had to use in the past. Yeah, let's talk about one of those workarounds, log transformation. We've all done it, right? It's a trick to make the model pay more attention to the low flows. And it does, but it comes at a huge cost. Look at these charts. See the red line from the log transformed model? It does okay with the low flows, but look at the highest flood peaks. It consistently, systematically underestimates them. It's a dangerous trade-off. Meanwhile, the blue JKGS line gets both the high flows and the low flows right. No compromises. And so, the paper's final recommendation is refreshingly clear and direct. They argue that a specific version of this, the augmented JKGS with a 30-day window, should be the new default, the new starting point for all of us doing hydrological modeling. In the end, what I love about this new approach is the philosophy behind it. It's about being humble. It's about admitting our old, rigid assumptions just don't cut it anymore. Instead of forcing our view onto the data, this metric is designed to, as the authors so perfectly put it, let the data speak for themselves. And that kind of leaves us with a much bigger thought, doesn't it? We're talking about hydrology today, but we're not the only field dealing with a world in flux. So if our most basic assumption, a stable climate, is officially off the table, what other scientific rulers and yardsticks that we rely on every day might also be broken? What other moving targets do we need to start modeling?
highly dramatic, but I was actually quite impressed by the how do I stop sharing? I was actually quite impressed by the quality of the uh, extraction of ideas from
The
the.
the figure caption or the description of the figures, including like in this dip here during the arid region. I know that all was probably in the text, obviously. So
Some of it was not in the text. Some of it actually went beyond the text and inferred from general knowledge context, I think.
yeah, it's amazing. It's amazing what can be done automatically. I mean, yeah, it's super dramatic, and I'm on, I'm getting pretty sick of everything being crucial and game changing, but
Right,
uh like if someone had put this together like, 10 years ago, it would have been seen as like extremely high quality content, right?
right. How do I stop sharing, guys? I, I don't have a button to stop share anymore. Anyway, um, so we got another 3, 4 minutes. Any other thoughts, questions, suggestions for Jawad?
Could you share the video?
Oh, sure, sure.
It's so
I
dramatic that I want to share with the students. This way,
okay,
wow, yeah.
okay. Yeah, go play with Notebook LLM. I'm really quite impressed. I've been taking other papers and sticking them in there, and you can play with the prompts. And, you can tell it what kind of a video you want and
Do you
so
need a
on.
subscription?
We get it for free from the university because we have a Google, whatever uh, connection. But I think you can also get a subscription if you want. But Marie, I think, told me you can do it with cloud. The same kind of things are capable. It's just Notebook LLM is sort of targeting, you know, like one of the things I did was what did I do? I had it go to. You guys know Rush is getting back together again with a new drummer and the touring, the Canadian band Rush.
That's crazy. I can't believe it.
Yeah. What's her name? It's a young girl, actually, a really good drummer. Anyway, so I had it go and download all the websites related to the Rush tour, and I had it prepare a map of all the cities in the world where they're going to be touring, with an arrow going from one to the other.
Hmm.
Let me show you. Oops.
Are you gonna follow them, Hoshin?
Uh, that would be interesting. Let me sorry, I got to turn off my blur. Oh, there we go.
Hmm.
So it actually prepared this map for me.
Yeah.
And there are problems. It got the dates wrong and so on and so forth. But it's amazing what
Hmm.
agent-based. We had this conversation last time where we were saying, people are saying large language models is the major new technology, and I'm saying no, it's agents. Agents based on large language models are the major new technology of our day because you can go shopping now. ChatGPT allows you to go shopping, right? Um, and you say, I want to buy this and find me the best price, or I want this, I want to fly to such and such place, go check out all the sites and come back. So you used to have to get an app for that. Now you can just go to an agent.
I was just talking with the USGS before this meeting, and talking about like what they want out of graduates, to get hired. And this comes up again and again where they're like, well, everybody needs to have AI training now. And I was like, well, like, what do you mean? You want them to build AI models? You want them to use AI? And it wasn't quite clear, but I think using AI agent, like figuring out how to use agentic systems is like that's the federal government employees are now going to be expected to like build agents to do things like that.
There's actually a good article online. Maybe I'll send it around. Um, by this woman who was, saying everybody's concerned about the fact that, you can cheat and, they're concerned about the fact are students going to learn anything in the classroom if they can just go and, you know, put instructions in and get an answer back out of the agent. It's a pretty good article because she took that thing seriously and she redesigned her class entirely around allowing students to use agents and the web and so on, and says that the class completely changed from being one of knowing how to do things to thinking about what you need to do. In other words, it's about framing the problem so that you can do proper prompting and then
Mhm.
evaluating the results and so on. So in a sense, you're using your brains to contextualize and formulate the problem, which arguably is really what we want students to learn, right?
I totally agree. I just wonder if they need to have some what level, and not that they need to, what level of foundation do they have to have before they can do that? Because you can't. Well, maybe you can. Maybe if you just have them start prompting in kindergarten, you never know. But
I mean, it's a little bit like Star Trek, right? Where you can talk to data, or you can talk to whatever, the human is still in the loop,
Mhm.
um, because it's choosing what to focus on, choosing, it's like, but the machine is acting as a pushback, if something doesn't match the theory or something doesn't match the data or something like that, it can act as a pushback and force you. But of course, if you want to be lazy, you can be lazy, right? It's like,
Well, I thought you were gonna mention Star Trek for this precise example where they don't like Starfleet doesn't need for money because everyone has the comfort of life they can expect, but people still go to work because they switched to a paradigm where everyone's trying to improve themselves and not survive anymore, which maybe we're getting to that. It's a little bit like what's explored in Wall-E, I think, too, that cartoon that's like 10
Mhm.
years
yeah, more than 10 now, I think. Yeah. Humans did the thinking. Yep. Well, I don't think machines will not do thinking. I think machines are doing thinking. It's just that,
Oh shit, I gotta go.
all right,
Yeah.
take care, Jonathan. It's just that when I was growing up, I could go and take a class on how to fix my car, right? Now, probably, it's, I mean, yeah, I could take a class on how to fix my car, but so many of the components are electronic and so on. You just take the thing and switch it out, right? You, you know, you probably could grind the bore of the engine and, you could do all of this stuff. Um, I remember being in class when they said you can't use calculators uh, to do your exams. But of course, that went away pretty quickly. You had to use slide rules, and now very few people know how to use slide rules. Um, so this kind of shifts, and you could say the same thing. You take me and you drop me off in the middle of the desert, or drop me off in the middle of a jungle, and I don't know how to survive, right? Because I've lost that kind of content with nature and so on.
Yeah, I think in some way we have to evolve to kind of go to the next level of thinking. So, but in this process, probably we are going to have a lot of people that is going to be lazy in the sense that, okay, the machine is doing that. But for sure, it's a learning process. We need to go to the next level.
I mean, music is a good example because now all these companies are trying to train you to not care about the music and just use it in the background and not care about the band and the artist uh, and so on. But there's still pushback because people really care about seeing a band play live and they care about the creative process. and so on. It's just that the people making money are trying to, you know, trying to train you to not care. But on the other hand, you know, punk punk rock came out of people pushing back against the radio stations trying to control all the music, right?
So are we talking now about I had another meeting, so I missed it. But are we talking about that these AI tools, because they're so good at what they do, is that humans rely on them so much that they start to that fewer and fewer people actually know how things really work. Um, yeah, that's I'm very concerned about that because it is my ultimate belief that to do something fundamentally new, you can only do that if you really understand how something works. That's the only way possible. Maybe you have there are people that can come up with something completely new, just very intuitively without really understanding. But in my view, that's impossible. Once you really understand how different things work, so if most people lose that ability, and that is so easy with these AI tools. I mean, I'm confronted with it the whole day. If it's about computer coding, right? You write a simple script, and then you just ask AI, can you add this? Can you add this? Can you add this? And then it will add lines of code for you. But I don't know all these functions necessarily. Maybe I use 80%. So it uses already some functions that I don't know exactly anymore. Whereas a year ago, if my colleague would ask, Jasper, how did you improve that? I would be able to sit down and go in every little detail. But now you start to realize already, hey, I can explain 80% of, and that's just a simple coding thing. And that obviously over time, if you see its abilities, it's getting worse and worse and worse. And what worries me is that in the whole scientific world, we don't really talk about this, but I'm pretty confident that people review papers with ChatGPT, that people get the reviews, they feed them to ChatGPT, ask ChatGPT, how do I revise my paper? ChatGPT does the work. So ultimately, what we can go to the beach, computers are are doing the work. Like, what is our role? And I think it should be way more explicit in the preparation of a paper what the role of AI was. Because that contribution gets larger and larger and larger. And to me, that's not clear. And Jonathan and I talk about it a lot, and that is a lot of people are really don't want to talk about it, that they use AI. They're really, really not comfortable saying how they used AI. I mean, we all know, we can talk about AI will write you a reference letter. AI, you feed a figure and you ask, can you write 2 paragraphs for the paper? It will write 2 paragraphs, and then it's just an iterative process. So you barely, and so we need to, I think we need to really talk about this in terms of what that means for a scientific publication, because arguably, I told several times that we should add ChatGPT as a co-author, because arguably it did more on papers than many other co-authors, right? So, but yeah, if you do that, anyway, I feel that with these big companies developing these tools, that we're not we're not in control. Like the next thing comes out, the next thing comes out, and I think a lot of people are struggling to get some level of control. Where's this heading? What do we do? Education, what do we do? So a lot of questions that, yeah, I I would love to talk to people about this, how we can, yeah, do this in scientific publication. How we make explicit how AI was used, what is its role. Um, because otherwise we're just computers do the work, and then we submit the paper to a journal and it's being reviewed by a computer. Then yeah, what are we doing?
I think you're absolutely right that this is going to provoke a rethinking of education and so on. Um, I don't know if you know, there's a guy by the name of Tony Robbins, neurolinguistic programming.
Yeah.
And he runs these workshops called Mastery University. I actually attended many, many years ago. And what's interesting is he basically says there's a whole bunch of stuff. When you go to school, they teach you certain things, but really what they teach you mostly is how to do things, right? How to multiply two numbers together, how to add numbers, how to right? It's mostly about the execution. And if you get some training in how to think along the way, then that's great. But the way it tests you is not on whether you think, but on the execution, right? And even the testing is how do you do this experiment to generate hydrogen sulfide, right? Whereas a form of thinking would be, I give you this chemical and I give you this chemical and give this chemical and I mix them together. Tell me what's going to happen, right? For that, you have to know how to think. Instead, they ask you the question is, tell me the experiment. What do you? So you just have to memorize everything and regurgitate it, right? Um, and the nice thing about so Tony Robbins made his whole thing on the base. I'm going to teach you all the things that they should have taught you in school, but they didn't teach you. Like what's important about your health, how to manage money, you know, how to, various kinds of things which are all life skills. But you go to
Yes.
school and they
Yes.
say there's not, how to cook,
Yeah. 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 Yeah.
how to interact with people, right? These are,
Yes.
yeah. So our
Yeah.
educational system has become very much one of we're going to teach you how to pass the test. Yeah.
Yes. No, it's remarkable, Hoshin, because I was talking to my wife recently. Yeah. I grew up, my father was a principal, 15 schools. My mom was an accountant. And I, went to high school. We got economics. But I was always of the idea that if you want to start your own business, you first build money on a bank account, then you have an idea, then you spend that money, you get a few people, you have an idea, you build a product. And only until very recent, um, I suddenly realized, oh, but there's something like there are investors. You sell them an idea and they say, here's $1 million, milestone one, and then we'll talk again in half a year. So, and I knew that that existed 10, 15 years ago, but didn't know that when I was 15 years old. And I think these are really important things to know at an early age, stock market, how these things work, because there are many ways then that you can actually. I think that there are a lot of people that have a really great idea, but they don't know the access how to accomplish something. Um, and I remember having a friend, Hoshin, he went to MIT. We were both chess players, and one day there was in Amsterdam. Was a professor from MIT visiting. He said, "I'm looking for new PhD students." Professor there said, "He's a really good student." He went to MIT. After 4 years, he finished his PhD, and he said, "Jasper, academia is really not for me." I said, "I can reproduce, but I am not innovative. So if you give me a new problem, I cannot solve. I can solve existing problems based on all the theory, and I think that's an element in life, improvisation. That like how are you able to do something new? That's not taught in school. Like what you usually see is that a lot of kids, certainly going to academia, they're really good with theory. Once they have to build something with their hands, they fail. They're not really good with their hands doing experiments. They can do theory. Some can do both, but I think that aspect of life being proactive. I had a friend, brilliant friend, but he has a very simple job. He's really happy. But why? Because he was not proactive. He always expected the world would come to him, right? Whereas that's also a skill, like that you go out there, right? We know people that go out, go talk to people, and that's where you build connections, and that's when you get things done. What politicians do, right? The grassroots. Now, I think a lot of these skills are absolutely not taught at elementary school or middle school, high school. Impro.
I highly recommend this book. It's written by this guy, Keith Johnston. It's called Improv. Forget about the improvisation theater. That's part of. This is the guy who invented that sequence of things that were used in the Canadian show Whose Line Is It Anyway? Do you remember that
Okay, yeah,
Canadian?
yeah,
Yeah.
yeah.
Improvisational theater where so he created all the games that they play. He was a school teacher and he was teaching young kids and he quit teaching. He was teaching art because he realized that as the kids were going through school, their creativity was being killed. They were
Yes,
being
yeah.
trained to be less and less and less creative. So he quit and he went and he started exploring improvisational theater. And he asked the question, if I'm sitting down with you and I'm having a conversation, um, and you say something, I just answer back, right? And we have a concept. We're improvising. we're not thinking about, there's no ego getting in the way, there's nothing. You take the same people, you put them on stage, and you say, okay, you're a baker, you're a plumber, you're whatever, have an interaction, and all of a sudden they freeze up,
Mm-hmm.
right?
Mm-hmm.
And this is the same thing when you go to Zen training. The Zen master asks you a question, and you freeze up. I don't know what the answer. What's the right answer to the question? You go on stage, you go, oh, what's the right thing? What am I supposed to say? Right?
Mm-hmm. Mm-hmm.
So he invented these rules like whatever the person says, you agree with it, and then you continue, right? You don't say no, for example, and so on. And what I realized is it's basically all the same thing. It's basically getting out of the way of this natural creative process and saying,
Yes. Yeah.
no, I don't have to follow the rules. I can just
Yeah.
follow my natural following. And
Yeah.
science at its best is actually just improvisation, right?
Yes. Yeah.
If you have to write a proposal beforehand to get $300,000, you're telling them what you want to do.
Yeah.
But really, you just give me the $300,000, I will figure it out as I go along, and I will do much more creative work
Yeah.
if you force me to do only that thing that I wrote, because
Yes.
that's no longer new. It's no longer, it's no longer this creative process.
No, no, you're right. But I think the whole academic world, in some sense, it's really strange that you hire faculty and that you tell them you're evaluated on these five things. And I know a lot of faculty then just go down that list, like I need to do this, I need to do that. And to me, that is not what academia in its purest form is about. But
Sure.
that's how the system has become in large part. And that sometimes, yeah, yeah, yeah. Because, what's so interesting, I was listening to Steve Jobs, just random, and one remark. So he said that basically his success started when he realized that when you build a new technology or you have a new idea, right, and say it works, that if you then try to find an application for it, that is not the way it really works. You said you need to think 10 years ahead, the customer experience, he calls it. Like, what do people want? What would be like, and I think we can have this conversation in hydrology. Where does hydrology need to be in 10 years, right? What is it that we want to do? And then you build the technology to get to that point, the other way around. Instead of having first, do all the things that we're doing, solving incremental problems. What can we do with what we have? But think more, what is it that people would want to do 10 years from now in terms of hydrology? And then you build the technology to make that possible. And once he made that switch, I think most of us we're working on something small, and then you try to find an application, writing proposals. But I think you need to think bigger, and this is where creativity comes in. But yeah,
In a way, I'll bring it back to Jawad's thing. In a way, it's being willing to follow a non-stationary benchmark. Tomorrow is not going to be the same as today, right? You
yeah,
just got to keep following the new things as they change. All right, guys. Thank you so much for the conversation. Thank you, Jawad, for the presentation.
thank
Luis, I
you.
will send you a link to the. I'll have to put it. It's big, so I'll put it on a. I'll send you an email, and you probably have to download it from somewhere. Um, but just let me remind you, 3 weeks from now, Jasper will talk about the SAGE algorithm. Hopefully, Jonathan will be there also to help answer some
Is it 3
questions.
weeks? That's during hydromel, Jose. I thought we skipped
Oh,
one.
okay. I'm sorry. So yeah, you're right. 3 weeks from now, there will not be get together because it's over the week of Hydromel. So we'll skip that, and then it'll be 6 weeks from now. Yeah. All right. Anyway, nice to see everybody. Thanks for joining, Song Kung and Yuan. Even though I didn't see you guys.
So
Good
So
job, Jawad.
yeah.
Bye bye.
Bye.
All right.